Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 11th graders 2002, problem number 2. Let AK be the point with coordinates k and k cubed for any non-negative integer k. Part A. We wish to prove that for any distinct non-negative integers kl and m, points ak, al, and am are not collinear. They are not on the same line. And for part B, let B be the point 0, 1, and let O be the origin. We wish to prove that the measure of angle A, K1, OB, plus the measure of angle A, K2, OB, and so on, plus A, Kn, OB, is strictly less than pi over 2 for any integers K1, K2, and so on, distinct but positive integers. So it's a nice problem, especially part B. So here are my hints. First, recall that points x, y, and z are collinear if and only if the determinant, so we make two vectors, and the determinant of these two vectors should be equal to 0. If this is the case, they are collinear. If it's not, they are not collinear. And for part B, instead of points 0, 1, and k cubed, consider points 1, 0, and k cubed k, and use complex numbers. And recall this fact that if we have complex number z, written as x plus y times I, where x is greater than 0, then we can get the argument of this complex number by using just the arctangent function of y over x. And also, we'll use these facts that arctangent of u is bounded from above by u, for positive numbers u. And also, we will make use of the following fact that the series from k equals 1 to infinity of 1 over k squared equals pi squared over 6. Well-known fact, first proven by Euler, I believe. And also, when estimating the series of arctangents of 1 over k squared, separate the very first term from the rest and apply our inequality and apply this identity with pi squared over 6. So give this problem a try. Alright, so let's do it. So for part A, let's start with part A. Part A, let AK be equal KK cubed, AL equals L cubed, AM equals MM cubed. What are the vectors connecting them? Well, then, let's take a look. Then, vector AKAL, it's L minus K, L cubed minus K cubed, and this can be factorized, and we'll get L minus K, and we'll have vector 1, K squared plus KL plus L squared. Basic factorization. Likewise, AKAM, this vector is M minus K, M cubed minus K cubed. Again, simple factorization, it's M minus K, 1 K squared plus KM plus M squared. Alright. And now let's compute the determinant of these two vectors. The determinant of AKAL and AKAM. Well, notice that here we have L minus K, here we have M minus K, so we can already put it in front of our determinant. And we have the determinant of 1 K squared plus KL plus L squared, 1 K squared plus KM plus M squared. Alright, and now computations, L minus K, M minus K, and now here I have, we subtract this from that, and we'll have, after some simplification, we will get M squared minus L squared plus Km minus KL after simplifications. And notice that we can do factorization. because we can write the following. We can write here we have m plus l times m minus l, and here we have plus k m minus l. So it's l minus k, m minus k, m minus l, k plus l plus m. Very nice. And notice that, of course, this is not 0. This is, of course, not 0 because k, l, and m are non-negative integers, and because they are pairwise different. This is not 0, this is not 0, this is not 0, and this is positive. So no problem there. Alright, which closes the proof of part A. Now, for the part B is more complicated. Recall that we have our points ak equals k cubed. We have our origin, which is 0, 0, and we have our point B, which is 0, 1. Right. Now, I wish to consider the following points: ak tilde, 0 tilde, b tilde. They are just points written above, but with coordinates exchanged. We have k cubed, k, 0, 0, 1, 0. And notice that, of course, we have that the measure of angle AKOB is, of course, the same as the measure of angle AK tilde O tilde B tilde. All right. Now, let's use complex numbers. Let's draw our points. Here we have point 0, 0. So it's point O. Here we have point B, 1, 0, B tilde rather, B tilde. And these points AK, they lie on the graph of cube root. Should be visible. So for example, here we have A1 tilde. We may say that somewhere there is A2 tilde, and so on. We are considering the measures of these angles right here. And we wish to show that if we add every such angle together, we'll get a result strictly less than pi over 2. And to do that, we'll use complex numbers. Because notice the following. Series from k equals 1 to infinity of measure of angle AKOB. Well, notice that we are in the first quadrant, and these angles are just the arguments of points AK tilde. Argument of point AK tilde, of course, viewed as a complex number. All right. And how can we find this argument of this complex number? Well, since we are in the first quadrant, this is just the arc tangent of y over x, so of k over k cubed. So in other words, it's series from k equals 1 to infinity of arc tangent of 1 over k squared. Now, arc tangent of u, maybe let's write it here, arc tangent of u is always strictly less than u or u greater than 0. Yes, but if I simply replace this series by series of 1 over k squared, our result will be too big. This estimate is not accurate enough. And I wish to do the following. I wish to change this series to go from k equals 2, and I wish to take the first term separately. First term separately. Alright. So we have the following inequality. What is arctangent of 1? Well, of course, arctangent of 1 is pi over 4. It's pi over 4. And this series can be replaced by series from 2 to infinity of 1 over k squared. Alright, and now I wish to do the following trick. I will subtract and I will add 1. So I will sum from k equals 1 to infinity of 1 over k squared. So I have introduced term with k equals 1, so I subtracted 1 as well. Now I will use this powerful result. Maybe let's write it right here. Series as k goes from 1 to infinity, 1 over k squared happens to be pi squared over 6. So this whole series is pi squared over 6 plus pi over 4 minus 1. And the only question remaining, is this less than pi over 2? Is it? Well, notice that this is equivalent to saying, after some manipulations, it's equivalent to saying that pi squared over 6 should be less than 1 plus pi over 4. And this, in turn, is equivalent, after multiplication by 12 or by 6, to saying that pi squared over 6 is less than 6 plus 6 over 4 is 3 pi over 2. And by basic calculations, you can verify that this is indeed the case. This inequality is true. It is true. So, which means that for any 0 less than k1, k2, and so on, kn, the measures of angle AK1OB plus the measure of angle AK2OB and so on, AKNOB is strictly less than pi over 2, which closes the proof of part B, and which closes also our video. Very nice problem, I say. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.